All right, let's take a look at more examples of infrared spectra of different compounds. We have this IR spectrum. We've seen it before. It's the IR spectrum of the alkene with a 6-membered ring. There are a number of other features that I want to point out with respect to this spectrum. Moving from left to right, we come to this small peak. As we pointed out, this peak is caused by the alkenyl CH bond undergoing a stretching motion, absorbing infrared light. It occurs at about 3050 wave numbers. Now, one thing to realize about this peak, though, is that it's sharp but relatively small compared with other peaks in the spectrum. Why is the peak small? Well, in general, the size of a peak is determined by the number of photons that get absorbed. A bigger peak means more photons absorbed. A smaller peak means fewer photons are absorbed. We mentioned already that a requirement for a vibrating bond to absorb a photon is that it undergo a change in polarity during the course of vibration. If the change in polarity is large, then it is more likely that a photon will be absorbed, more likely that a photon will latch on to that bond. So that if we have a given bond whose change in polarity is large, we're going to see more photons absorbed by it, resulting in a larger peak. On the other hand, if we have an oscillating bond changing its polarity, but let's say the change in polarity is not large, it will still absorb photons, but will not absorb as many photons. The probability of absorption of photon is less. So in that case, our vibrating bond will produce a peak, but that peak will be relatively small because fewer photons get absorbed. That turns out to be the case of our alkenyl CH. There is a change in dipole moment, but it's not a large change in polarity, resulting in fewer photons absorbed and a smaller peak. Here we come to the IR spectrum of an alkyne. Note the carbon-carbon triple bond, and attached to it is an ester group. This is a structural abbreviation. It's a C double bond O, single bond O CH3. The peaks in the spectrum are identified according to the functional group producing them. This first peak we encounter here from left to right is an alkynyl CH stretch. The next peak we encounter is a peak for the carbon-carbon triple bond stretch. We note that this peak is sharp and relatively big. And that's because if you examine the molecule, there is a relatively larger polarity to it. The ester group is very electron withdrawing, pulls electrons compared to hydrogen. And that creates a polarity, a significant polarity in the CC triple bond. Now when the CC triple bond stretches, that polarity gets even larger. So there's a relatively larger change in polarity as the CC triple bond stretches and compresses back and forth. Hence, the stretching motion of our CC triple bond here is fairly large. On the other hand, if we were to examine the absorption peak for the carbon-carbon triple bond stretch of a different alkyne which had nonpolar groups on it, what we'd find is that that peak would be a lot smaller because in that particular case with nonpolar alkyl groups there isn't a very large change in polarity during the course of the vibration. Now, one of the bigger peaks is this peak here. It is located about 1720, and it's caused by the absorption of the carbonyl group undergoing a stretching motion. The C double bond O stretching. You mentioned that that C double bond O stretch produces fairly large prominent peaks. What that means then is that during the course of a carbonyl stretching motion, there's a significant change in polarity producing a larger peak, resulting in more photons being absorbed. Now these peaks on the right are bending peaks. The next spectrum. This spectrum is not the complete spectrum. It's of nitrobenzene. And one thing to point out with respect to this spectrum is the peaks for the aromatic ring. Now it also mentions the nitro group, but I don't want to focus on that so much. This is the structure of a benzene ring, and there are hydrogens at the various carbons. They're not shown. Those aromatic hydrogens, those CH bonds, undergo a stretching motion, and that stretching motion absorbs photons at a frequency between 3000 and 3100, though unfortunately that's not shown in the spectrum here. But also you have the carbon-carbon bond which will undergo stretching motion, and that we can see in the spectrum. If you recall, the CC bond stretch for an aromatic ring produces generally two peaks, sometimes three, a peak at 1500, a peak at 1600, and then sometimes at 1450. We can see those peaks in the spectrum. This peak here is at 1600, and there is a peak here which is 1500, although I don't see a 1450. So the peak here are associated with the aromatic CC bond stretching motion. The next spectrum. This spectrum also has an aromatic ring, though it also is not the complete spectrum. It has a hydroxyl group, so there's two features in the spectrum that we'll want to examine. Two features that correspondingly will produce peaks. Well, the biggest peak here is this relatively broad peak, centered about 3500. That's due to the OH stretch of this alcohol. Remember we mentioned that alcohol groups, the OH group, produce a peak that's relatively broad. The broadening is due to the existence of hydrogen bonding. There are various degrees of hydrogen bonding of the compound in its solution, and that produces some different absorption frequency, producing kind of a range, producing a broader peak. Now the benzene ring, the aromatic ring, has hydrogens, and they undergo stretching motion. Those stretching motions occur between 3000 and 3100, and there is the peak that they produce right there. The CH2 peak is the alkyl CHs undergoing stretching motion. The next spectrum. This is a spectrum of an aromatic aldehyde. This group is a structural abbreviation. It's kind of hard to see what it is, but it's a carbonyl group with a hydrogen attached to the carbon. It's an aldehyde group. We mentioned that aldehydes, the CH stretch, produces two peaks at 2720 and 2820, and there they are, the peak here and the peak here. 2820, this peak here, 2720. Those are produced by the aldehyde CH stretch. Now of course there's a carbonyl group. We should see a big peak for it, and indeed here it is right here. This big peak is associated with the C double bond O stretching motion. The next spectrum is of a carboxylic acid. There's a little glitch in the structural formula. This is an abbreviation for the carboxyl group. there's a C double bond O OH. The symbol H is partly cut off here. Now, let's take a look at the peaks. One thing we mentioned is that the carboxyl OH group, the stretching motion that it has, produces a very, very broad camel's hump type of peak. And here it is right here, starting out about 3,500 and moving all the way down to around 2,500. This right here is one peak. Now it's superimposed by the peak here, which is due to the CH alkyl stretches. There are lots of CH alkyl bonds in this molecule. In the carboxyl group, of course, there's a carbonyl group producing the carbonyl stretching motion. That carbonyl stretching motion produces the prominent, fairly large peak here, and it's going to be around 1720 or so. The next spectrum, this also has an aromatic ring, and it has an amine group, an NH2. It's an amino group. NH stretches occur about the same place as OH, around 3,500. One characteristic of the NH2 group is that it produces two peaks. They're called a doublet. And it's due to the stretching motion of the NH bond. Notice that in contrast to OH peaks, the NH peaks are not nearly as broad. And that's one way you can distinguish between an amine and an alcohol. The amine NH peaks, they're in about the same place, are not as broad as the hydroxyl, the OH peaks. All right. Now the aromatic ring, let's take a look at it. The CH stretches of the aromatic ring, we should see something above 3,000, and well, it's there it is. The peak is kind of squished a little bit, but that peak right there extends over 3,000, and indeed that's going to be caused by the aromatic CH stretches. Now we should see a band at 15 and 1600 for the aromatic ring. Now that's probably the shoulder of this bigger peak. This NH2 is actually identified as a band, but you can notice it has a little shoulder here right at 1600, and that undoubtedly is due to the CC stretch of the benzene ring. We should see something at 1500, and there we have it right here, 1500. That's the other peak that we see for the CC stretch of a aromatic ring. And here we have the 1450 peak.